Hello and welcome to another Mr. Marriott Maths video. This time we're attempting question 8 of the October 2021 decision maths paper by Edexcel. And Susie's preparing for a triathlon event that is taking place next month. And the triathlon involves 3 activities: swimming, cycling and running. Susie decides in her training next week she should maximise the total time spent cycling and running, train for at most 39 hours, spend at least 40% of her time swimming, and spend a total of at least 28 hours of her time swimming and running. And Susie needs to determine how long she should spend next week training for each activity, where X is the number of hours swimming, Y is the number of hours cycling, and Z is the number of hours running. And it has to formulate the information as a linear programming problem, where we have to state the objective and list the constraints as inequalities with integer coefficients. So let's try and list the objective first of all. We want to maximise the total time spent cycling and running. So we want to maximise a variable p, and p is consisting of a time spent cycling and running. So we're maximising y plus z, as that represents the time spent cycling and running. And we've got some conditions. It's going to be subject to the following conditions. We train for at most 39 hours, so the time spent training, x plus y plus z, is smaller than or equal to 39. We want to spend at least 40% of the time swimming. So the time spent swimming, which is x, is greater than or equal to 40% or 0.4 lots of the total time, x plus y plus z. This isn't going to give us integer coefficients, and this isn't simplified, so we're going to try and get integer coefficients now. I'm going to multiply everything by 5. So we're going to get 5x is greater than or equal to 2x plus 2y plus 2z. And I'm going to get everything onto one side of the inequality. I could get everything onto the left-hand side and be greater than or equal to a number. But I could get everything onto the right-hand side and be smaller than a number, and I prefer that. So I'm going to subtract 5x from both sides. So I'm going to get that negative 3x plus 2y plus 2z is smaller than or equal to 0. We want to spend a total of at least 28 hours of her time swimming and running. So the time spent swimming and running, which is x plus z, needs to be at least 28. So we've got our 3 constraints as simplified inequalities. Got x plus y plus z is less than or equal to 39. Got negative 3x plus 2y plus 2z is less than or equal to 0. And we've got x plus z is greater than or equal to 28. So how would the marks have been awarded for this question? Well, we've got an independent accuracy mark for giving x plus y plus z is less than or equal to 39. We've got an M1A1, a method mark and an accuracy mark for this inequality here. An independent accuracy mark for x plus z is greater than or equal to 28. And then an independent accuracy mark for p is equal to y plus z. Although we do need to rearrange p in order to apply the simplex algorithm, we need to rearrange it to get p subtract y subtract z is equal to 0. Susie decides to solve this linear programming problem by using the 2-stage simplex method. We want to set up an initial tableau for for solving this problem using the two-stage simplex method. We want to show how the constraints are being made into equations using slack variables, exactly one surplus variable, and exactly one artificial variable. And we want to show the rows where two objective functions and how they're formed. We've already shown how the row for the profit or the P objective row has been formed, but we do have another one because we're using the two-stage simplex method. So, part B, we have P subtract Y subtract Z is equal to 0. We're going to have X plus Y plus Z plus a slack variable S1 is equal to 39. We're going to have negative 3x plus 2y plus 2z, subtract a surplus variable S2 plus an artificial variable A1 is equal to 0. My apologies, no, this is a smaller than or equal to inequality. We're not going to have that. We're just going to have plus a slack variable S2 equal to 0. It's the next one where we're going to have the surplus variable and the artificial variable. We're going to have x plus z, subtract a surplus variable S3 plus an artificial variable A1 is equal to 28. So we've now got the four equations we would typically have for the normal simplex algorithm, but we also need to define our objective I. And I is equal to negative the sum of all the artificial variables, which in this case is just A1. So I is equal to negative A1, but we can't have artificial variables in the objective row for I because we've already got a 1 as a coefficient of A1 elsewhere. So we need to replace A1 with a rearrangement of the third equation. So we need to rearrange the third constraint equation to get A1. And A1 is 28, subtract x, subtract z, plus S3. So I rearrange this equation, I can subtract x, subtract z, and add S3 to get everything onto the other side. So I can now say that I is equal to negative 28 plus x plus z subtract S3. And I've finally got to rearrange this equation to get all the variables on one side and just the constant on the other side. So I'm going to get I subtract x subtract z plus S3 is equal to negative 28. So when I try setting up my table now, I'm going to put my three constraints in. So I've got basic variable S1, S2, and instead of S3, I'm going to have a basic variable A1. I'm going to get, for the basic variable S1, I'm going to have 1x plus 1y plus 1z plus 1s1 is equal to 39. I'm going to get negative 3x plus 2y plus 2z plus s2 is equal to 0. And I'm going to get 1x plus 1z subtract 1s3 plus a1 is equal to 28. And I can fill everything else in with zeros. Next up, I can put in my equation p subtract y subtract z equals 0. So p subtract y subtract z equals 0. And I can put in my equation I subtract x subtract z plus s3 is equal to negative 28. And I'm going to fill in all of the other cells with zeros. So how are the marks awarded for this question? Well, for the two equations that use slack variables, rewriting those as equations would get an M1, A1. For the one equation that uses a surplus and an artificial variable that gains an independent accuracy mark, and then rearranging the I equation to get I subtract x subtract z plus s3 equal to negative 28 would gain a method mark, an M1 mark. And the mark for p subtract y subtract z is implied from part A. And then setting up the table, there is a method mark and an accuracy mark. And the method mark is for getting 2 full rows correct. And the accuracy mark is for getting all 5 rows fully correct. So that's another 6 marks. We've already seen 11 marks just for setting up the two-stage simplex method. We're now told that the following table T is obtained after one iteration of the second stage of a two-stage simplex method. So, if this following table has been obtained after one iteration of a second stage, we're asked to obtain a suitable pivot for the second iteration. So you just want to find the next pivot. So let's try finding the next pivot, and we need to give reasons for our answers. So the only negative in the objective row is the -1. So a pivot is from the Z column. So our pivot column is Z. So only negative in objective row is from the Z column. Which implies that the Z column is the pivot column. And then if we calculate our theta values, we're going to get infinity, we're going to get 62/5, we're going to get 28, and we don't need to calculate a pivot for the objective row. So because 62/5 is smaller than 28, S2 row is the pivot row, which implies 5 in the S2 row is the pivot. So we're pivoting around this 5 right here. So you've got an independent accuracy mark for identifying the pivot column and an independent accuracy mark for identifying the pivot using the pivot row. And now we're asked to start from the table T provided, solve a linear programming problem by performing one further iteration of a second stage of a two-stage simplex method. So we just asked to do this second iteration. So let's try doing that iteration. So we need to make our method clear by stating the row operations we use. So first of all, we're going to use the pivot row, and the row operation is going to be row 2 is equal to a fifth of the old row 2. So we're taking a fifth of the old row 2. And when we do that, we're going to get 0, 0, 1, -2/5, 1/5, -1, and 62/5. And our basic variable, S2, is going to be replaced with Z. We now want to eliminate any other integers or any other values in the Z column to become 0. So row 1 can stay the same because the value in the Z column is already 0. So we're going to get Y 0, 1, 0, 1, 0, 1, 11. The X row, we now need to subtract one lot of a new row 2. So the new row 3 is going to be the old row 3, subtract the new row 2. So we're going to go along. 1 subtract 0 is 1. 0 subtract 0 is 0. 1 subtract 1 is 0. 0 subtract negative 2/5 is positive 2/5. 0 subtract positive 1/5 is negative 1/5. And a negative 1 subtract negative 1 becomes 0. Then last but not least, 28 subtract 62/5 is the same as 140 subtract 62/5, which becomes 78/5. And then row 4 finally, I need to get this negative 1 to become 0, so I'm going to take row 4. It's going to be my old row 4 plus one lot of row 2. So if I add 1 to negative 1, that becomes 0. So I'm going to do the same thing here. 0 plus 0 is 0. 0 plus 0 is 0. Negative 1 plus 1 is 0. 1 plus negative 2/5 is 3/5. 0 plus a fifth is 1/5. 1 plus negative 1 is 0. And last but not least, 11 plus 62/5 is the same as 55/5 plus 62/5, which is 117/5. So where do the marks come from for this question? Have we actually solved this question? We've not actually confirmed that just yet, so we do need to confirm that. So no more negatives in objective row. Implies that we are finished. So we need to state our values. We've got x as a basic variable equal to 78/5. We've got y is equal to 11. Z is equal to 62/5. And p is equal to 117/5. But we need to put this into context. So we spend 78/5 hours swimming, because x represents the number of hours swimming. So we spend 15.6 hours swimming, 11 hours cycling, and 12.4 hours running. And this does satisfy all of our criteria. We've got x plus z greater than or equal to 28. We've got x plus y plus z smaller than or equal to 39. And we've got 40% of our time spent swimming, 15.6 hours out of 39 swimming. So we've hit the exact boundary for all three of these. So all of our slack and surplus variables are equal to 0. And we've maximised the amount of time spent cycling and running, which is what the question wanted. We wanted to maximise the amount of time cycling and running. So we've essentially minimised the time swimming, which is exactly 40% of that 39 hours in total, which is excellent news. So how is this question marked? Well, we're going to go through that right now. So there's an independent accuracy mark for the pivot row correct, including change of basic variable. So an independent accuracy mark for this second row here. A method mark for having all values in one of the non-pivot rows correct, or one of the non-zero and 1 columns correct. It's either a full row correct or one of these columns correct, x, y, and z. An accuracy mark for using row operations correctly at least twice. An accuracy mark for having all values in your table and all row operations correctly stated. And last but not least, an accuracy mark for a correct allocation of training times And this must be in context. So if you just say x is equal to 78 fifths, y is equal to 11, and z is equal to 62 fifths, you would not get this final accuracy mark. But it's a really important thing in decision maths, is giving all your answers in context. So we've managed to make it through this 18 mark question in a full 18 minutes. So we've actually beat the 1.2 minutes per mark and marked it. So we have reached the end of this video. So until next time, thank you for watching and goodbye.